Greetings, Matt Roscoe here at the University of Montana, and a lecture on Section 4.1 Local Maximum Minima in our Calculus for Middle School Teachers course this summer at the University of Montana. So today I want to talk to you a little bit about what the second derivative can tell us, and a lot of this should come as no surprise because we've taken a graphical approach to what the derivative tells us, and so now we're going to simply generalize that in an algebraic sense. So I have a working example I want to work through and then talk about what derivatives tell us as a review, give a definition for local extrema and critical point, and then introduce what are called the first derivative test and the second derivative test. These are classic components to any course on differential calculus. And then we'll work through 3 examples at the end of the lecture. So let's do a working example first. Let's take a look at this function, 4x to the third minus x to the fourth plus 10. So classic polynomial. Let's go ahead and escape out of here and get into a picture of what do we have. So what do derivatives tell us about this particular function? Looks like I'm on the screen, all right. Let's go ahead and think about this. So f of x is equal to 4x to the third minus x to the fourth plus 10. I'll go ahead and make this bigger so we can see it now. The first thing I notice is it's not written in standard form. The cubic is in front of the quartic, so I'll write it in standard form as a polynomial first. Negative x to the fourth plus 4x to the third plus 10. Okay, so now I think of this as a quartic function with a negative leading coefficient, so we should see n behavior that does something like that. There might be some bumpiness here, but it's definitely a downward turning sort of function whose end behavior in the negative and positive sense should be going towards negative infinity. So let's take a look and see what we get for first derivative. So the first derivative is going to be, well, if we apply the sum rule, we can separate each one of these terms in the polynomial and take their derivative independently. There are some constant multipliers, and so I guess I'll go ahead and charge forward using the power rule. It'll be negative 4x to the third. Using the power rule and the constant multiplier here would be 12x squared, and the derivative of any constant is 0. So this would be our derivative function. And let's talk a little bit about what the first derivative tells us. Well, it tells us where this thing has a positive or a negative slope, where that function has a positive or negatively valued slope. So one interesting thing to do is always to find this idea of where the slope might be equal to 0. So how would we do that? The idea is that, well, I shouldn't say n, let's do dy dx equals 0. How do we solve that? Where is the slope equal to 0 of this particular function? Well, we just set its derivative equal to 0 and solve. So if we set negative 4x to the third plus 12x squared equal to 0 and solve, let's just think about how we might do that. Well, one thing I can see right away is that there is a 4 and that I can take out in front. So let's take that out in front. Why don't I take the negative 4 out in front? Then we'd have x to the third minus 3x squared equals 0. And then I notice that there is an x squared term common to both terms in this binomial. So it'll be negative 4 times x squared times, let's see, x minus 3 equals 0. So now I can use the product, the zero product rule that says, if I have one number times another number equal to 0, then one of those numbers has to be 0. That's the only way you can get a product of 0 is if one of the multiplicands is actually 0. So either negative 4 is 0, well, that can't ever be, or x squared is 0. Well, that can only happen when x is equal to 0. or x minus 3 is 0, and that can only happen when x is equal to positive 3. So what do we know about this function? At this point, what we know is we know that it has a 0-valued slope when x is equal to 0 or when x is equal to 3. So there's some sort of a spot on that function when x is equal to 0 or x is equal to 3 where the function is actually flat. Now think about what that means for a polynomial. You know, a polynomial is a continuous function, and so that must mean that it somehow curves and has this 0 valued slope when x is 0 or when x is 3. Okay, so that's kind of nice. We know a little bit now all about that function without even having looked at it graphically. So let me see if I can keep this on the same page. Can I do that? I think I can. All right. You know, but might be kind of interesting to take a look and see what the second derivative of the function is and see if that can help us. So we know what the first derivative is. The first derivative is, I'll go ahead and highlight it here in red. Here is our first derivative. So to find the second derivative, we just take the derivative of the first derivative. So that's going to be easily obtained. If we use the power rule again on the negative 4x to the third, we'd have negative 12x squared. And if we use the power rule on 12x squared, what would we get? We get 2 times 12 or 24x. And so this is kind of interesting because what does the second derivative tell us? Well, reviewing, we know that what the second derivative tells us is where this, let's go ahead and highlight where the function itself lives. It's right here. The second derivative tells us about the curvature of the function itself. So where the second derivative is positive, we're concave up. Where it's negative, we're concave down. So kind of an interesting idea here. We could actually find some interesting spots where the second derivative is equal to 0, but we're going to leave that for 4.2. But one thing you might ask yourself is, okay, well, what would happen if I used these values of x into the second derivative? What would that tell us about those particular points? So let's take a look. So what if I did something like f double prime of 0? Well, you know, if I put a 0 in here, I get negative 12 times 0 squared plus 24 times 0. Well, that's obviously equal to 0. Okay, interesting. What about if I put something like f double prime of 3 into here? Well, let's see. So that would be negative 12 times 3 squared plus 24 times 3. Okay, so what does that mean? That means that we have negative 12 times 9 plus 24 times 3, which is, let's get a number here, negative 12 times 9 plus 24 times 3. Negative 36 is what we're getting. So at this point, where x is valued at 3, we have a negatively valued second derivative. So what do you think that tells us about this particular point on the graph? I'll just let you think about that for a second. What does that tell us about this particular point on the graph? And what does a 0 second derivative tell us about that point on the graph? That's another interesting question to think about. Okay, so hopefully you had just a second to think about that. Let's go ahead and see if we can kind of intuitively sketch a graph, and then we'll go to technology to get a sense of what this function looks like. Well, we obviously know that there's some action happening at 0 and at 3, right? So let's go ahead and put the function into the calculator and find out what f of 0 is and what f of 3 is. So if I put 0 into the function, I can see quite quickly that 0 minus 0 plus 10. So f of 0 is 10. Now 3 is a little bit harder to evaluate, so I'll do that on my calculator. 4 times 3 raised to the third minus 3 raised to the fourth plus 10. So f of 3 turns out to be 37. So we've got kind of some information now about the graph. We should be able to get a kind of a rough intuitive sketch of what the function looks like. And let's see, I'm sort of running out of room. Should I try it? I guess I'll try it on here. Let's take a look at what we think this function might be. So here would be y, here would be x. So right away, what do we know? Well, we know that the function passes through 0, 10 and 3, 37. So let's see here, 1, 2, 3, 37. So we got to go up to at least 40, I guess. 10, 20, 30, 40-ish. So there's this point 3, 37, right? And then there is this point 0, 10 right here. And the question is what is the function doing here? So can we use what we know about first and second derivatives to get a sense of the shape of the function from here? Well, right away, the 337 should make sense that we have a pretty good sense of what's going on there. We know that the value of the slope here is 0, so I'm going to draw in little slope lines. The value of the slope here is 0. We also know the value of the slope here is 0. So the function, whatever it does, it has to come through that point and through this point and have some sort of a 0 valued slope. We also know that those are the only two places that the function has a 0 value slope. So everywhere else on the domain of the function, we have a non-zero slope. So we're either in negatively valued slope approaching this point, or a positively valued slope, but we're never a 0 valued slope approaching that point. Now we can use the second derivative evaluated at 3 to determine exactly what goes on at 3. We know that at 3, the concavity is negative. So in a sense, this is negatively or downward shaping graph. So I'll do it in green, or I guess I'll do it in blue since I use blue for my function up here. But I know that things have to come through that point and be downward turning, right? Some sort of downward turning, negative concavity. So that's interesting. We know right away that point 3, 37 is what we'll call a local maximum, that things are getting close to that spot from a downward sense and away from that spot in a downward sense because the concavity is negative. Now we don't have the luxury at 0, 10 to make the same assessment because of the fact that at 10 we don't have either a negative or positive concavity. This is kind of an interesting anomaly. It seems like it's not doing this, it's not doing that. So let's figure out what's going on at 10 by taking something just a little ahead and a little behind 10, 1 and -1, and evaluate those in the derivative. So if I put a 1 in the derivative, then I get -4 plus 12, which is 8. So that means that the slope after 0 is positively valued. So that means that the thing must be moving up in this sense from there because the slopes there are positively valued. And if I put a -1 in here, then I get -1 cubed, that's a -1, so a -1 times -4 is +4. And here, if I put a -1 in there, squared, I get a positive. So it looks like the derivative at -1 is also positive. So meaning that the slopes are positive before I arrive here. So I would assume that what's going on is that we're approaching this thing with positively valued slopes, but then we have to pass through 0 right there. So positively valued slopes passing through 0 valued slope, but then positively valued slopes again. So my guess at what this function looks like is that it has to look something like this. Let's see if I can get it right. Something like that is my guess. And the reason I know that, I mean, maybe let's make it completely clear. Well, I know that because the values of the slope are 0 at 0 and 3. So that's what the red lines are. I know that because the concavity at 3 is negative, so it must be downward turning at 3. And then at 1, or excuse me, at 0, I didn't have a concavity assessment. So what I did is I took a look at the slope before and after of that 0 slope and found out that both were positive, meaning that it has to approach that point from below in positively valued slopes, and then it has to leave that point um, heading above with positively valued slopes. So that's really the way that I figured that out. And what I've basically done is shown you what the first and second derivative tests tell us, and we'll generalize that in just a minute. But before we do that, let's take a look and see if technology backs us up. I'll escape out of here and minimize this, and then let's go into, I've created a GeoGebra file that you can, let's see if I can get that you can get out of the resources folder. But what the file does is it has a point on the function and the slope of a point on that function. And so you can see what the function is doing. It also shows you the x and the y for the function with dotted lines. And what's kind of interesting is that I've got some check boxes that you can add here. So the first one that you're going to want to be interested in looking at is where is the value of the first derivative 0? And again, it's at 0 and at 3. Those were the 2 points that we found analytically just by plugging them into the, by solving the first derivative set equal to 0. So those 2 important points turn out to be what we call critical points. So those are the points on the function where the value of the slope is equal to 0. So 2 critical points. And then you can carry out analysis for regions in which, if those are the 2 spots where they're equal to 0, then the derivative has to be valued positively or negatively in between those spots, right? And can't be equal to 0 anywhere. And they can't change, right? I guess they can change, but they can't change from negative to positive except by passing through a critical point. So in a sense, what's going on is everything to the left of 3, if you can kind of analyze the graph, everything to the left of 3 is positively valued in slope, and everything to the right of 3 is negatively valued in slope. So you can see that these transitions from positive to negative slope can occur only at critical points, but that they don't have to occur at a critical point. So as in the case of 0, that here we have a transition from positive to positive. It's just that it comes down to 0, passes through 0, and then grows back to a positive valued slope. So I hope that makes it clear that critical points are opportunities for what we call a local maximum or minimum, but they're not definitively local maxes and minimums. So it's a one-way implication, if that makes sense. It's necessary but not sufficient to be a local maximum or minimum for that point to be a critical point. Okay, so that's what the first derivative tells us. Another thing that's kind of interesting is to take a look, and we'll do more of this in the next section, where the second derivative is equal to 0. It turns out that if you solve the second derivative for 0, that you'll get these 2 points. And this is kind of interesting because what it does is it allows you to identify regions of the graph that have a positive second derivative or are concave up. So everybody see that that's concave up, and regions of the graph that are concave down. So what that means is that you know what the concavity of the graph is in a continuous sense anywhere along its path. So you can use that result to evaluate critical points. And now you can kind of see why one critical point was easily identified as a local maximum and the other one wasn't based on concavity. You can see that the first critical point, I'm going to go ahead and take that out. The first critical point occurs on a spot where the concavity transitions from negative to positive, and so it definitely doesn't seem like it's a local maximum because you're approaching from below and leaving towards above, and so that was just simply a flat spot in the graph and not necessarily a peak or a valley. The same is the opposite is true, sorry, for the location x equals 3. Here you can see that the first derivative is equal to 0. That's a critical point, but that the concavity, the second derivative, is negative, and so we must have a downward shaped graph or concave down graph, and that makes that point a relative maximum. Okay, I hope that's been instrumental in understanding what's going on with graphs and what the first and second derivatives tell us. Let's go ahead and formalize what we know. By the way, this is GeoGebra, and you can get a free copy of GeoGebra at the link on our site, or geogebra.org, and you could play around with this particular file, which is in the resource folder. So let's just review. What do the first and second derivatives tell us? Well, we know that if the first derivative is greater than 0 on an interval of a graph, then f is increasing on that interval. If it's less than 0, if it's negatively valued on an interval, then f is decreasing on that interval. Likewise, the second derivative tells us a little bit about concavity. If the second derivative is greater than 0 on an interval, then the graph's concave up on that interval. And if the second derivative is negative on an interval, then the graph is concave down on an interval. So what is a local extrema? Well, this is sort of a sort of tongue-in-cheek or shorthand version of what a local extrema is. But let's suppose that P is a point in the domain of f, so it's an available value of x that can be put into a function. We say that it has f has a local minimum at P if f of P is less than or equal to the values of f for points near P. Okay. And we say that f has a local maximum at P if f of P is greater than or equal to the values of f for points near P. So what does this mean in kind of a, I guess, a pictorial sense? Oops, I wanted to do this one over here. You know, if we have just a general picture of a function, let's say here's our function. It looks like here would be, let's say, P1 and P2. We would think of P1 being a local maximum and P2 being a local minimum. The reason we think that is that the values of f near P, right? If I'm near P, if I'm sort of in this region about P, then the values of f near P are less than f of P1. And so that's a local maximum because these little points are less than f of P1 in P1's neighborhood. The values of the function near P2 are all greater than if we sort of look at the values of the function here around this particular spot, then those values are all higher in a sense than f of P2. So here we'd think of this one as a local min. Okay, so that's the idea, or local extrema. And then what's a critical point? Well, a critical point is a value in the domain of f where the derivative is valued at 0 or where the derivative is undefined. These things are called critical points of the function. There's some confusion in the way we name these. So the value p, that is the x value, is called a critical point. Also named a critical point of the function is the point p comma f of p. So sometimes we think of them as a tuple. Other times we think of it as just the x value in the tuple. You'll see your textbook use both of those as examples of critical points, and I will mark correct whether you give an x or an x comma f of x as a critical point, so don't worry about that. But be aware that the value f of p is often called the critical value of the function. So, you know, it's the value of the function evaluated at the critical point of the function, or the p value of the function. Okay, well, let's talk about the first derivative test. Suppose that p is a critical point, so it's something where we have a zero valued or undefined valued first derivative. Well, then if f prime of x changes from negative to positive at p, then f of x has a local minimum. And if f prime of x changes from positive to negative at p, then f of x has a local max at p. So let's think about what's going on there. Um, and pull this up again, think about what's going on here. So first derivative test, let's draw a picture of a local. Let's say f of x looks like this. Then what would we think here? Well, if we put pictures of points here, we could kind of think about slopes. And we can see that everything to the left of the critical point, let's call it P, here the f prime of x is greater than 0. Do you agree that as things move up towards the critical point P, which we also sometimes call P comma f of P, and as we move away, we can see that all the slopes are negative, so f prime of x is less than 0. So if we transition from greater than 0 to less than 0 at a critical point P, then we know we have a relative maximum, right? That's the first derivative test. Tells us that if you just before the critical point are positive and just after the critical point are negative, then you must have approached from below and be returning down to below as you pass through the critical point. And the opposite, of course, is true for a relative minimum, right? So if we have an f of x that looks like this with a critical point P, let's say, along some x-axis, and that sometimes we call these critical points P comma f of P. Then we can see the same, I should say the reverse is true here, that if we pick a few points on this function and think about the slope, and pick a few more points along the function and think about the slope. So slopes there, I'm trying to draw, get a sense that these slopes are all positive. So here f prime of x is greater than 0 in this region to this side of the critical point, and f prime of x is negative, so it's less than 0 on this side. So just the opposite of what we have going on up here is going on down here. As we approach the critical point from below, from down here, negative, 0, positive. Well, so what that means is it must have a negatively valued slope be approaching the critical point from above, right? Because it's decreasing. And then it must be increasing function to the right of the critical point. And so that means that the critical point must be a relative min. Okay? So that's the pictorial display of what's going on there. And that's what the first derivative test tells us. And we use that in our opening example. And what does the second derivative tell us? Well, that's what we were using when we evaluated the 0.3 comma 37 in the opening example. If you look at concavity at a critical point, then you can tell right away whether or not the thing is downward or upward turning. So if f prime of p is equal to 0 and the second derivative is greater than 0 at a critical point, then what do we have is a local minimum, right? Because the thing's concave up. And if f prime of p is equal to 0, 0 valued slope, and f double prime of p is less than 0 or a negative concavity or downward concavity, then f has a local maximum at p. Let's see what that looks like. I want to make sure too that you understand that there is a third possibility here, that both are valued at 0. That was the case for 0, 10 for our opening example, and if that's the case, then the test is really inconclusive. You basically can't use it to find out whether you have a local maximum or minimum at that point. So let's take a quick look at a pictorial display of this quickly, and then we'll get on to a few examples. So again, if we have something like this, a critical point at p comma f of p, where this is some p value on an x-axis. Well then, if the thing has a if f double prime of p is greater than 0, concave up, then what we can tell is that p is a zero-valued slope. F prime of p is equal to 0 there, and f double prime of p is positive, so the concave up just it leads to the conclusion that what we have here is a relative minimum. So and the opposite here is if we have some value of p and some value of f of x that at p that we can think of as p comma f of p. And here we can see that at that point the value of the f double prime of p has got to be less than 0, so concave down, whereas here we had concave up, so that would give you a relative max. Okay, and then the third case is obviously where you get a zero-valued second derivative, and that's an inconclusive test. And usually, what you should be able to kind of intuit what's going on there. That means it's neither concave down nor concave up. So usually, what that means is that point is a point of transition for concavity, like we saw in the opening example. And we'll talk more about that in section 4.2. Okay, let's go ahead and talk about a few examples. So I want to try to get through 3 here and get a sense of what is going on. And we'll take a look at what these things tell us. So let's go ahead and try this first one. And let's just assume what we're trying to find are the local maximum of the following functions. And I'm going to use just analytic approaches. Of course, you can use your graphing calculator to back you up. So x minus 2 ln x, let's find the first derivative. The first derivative of x is just 1 minus 2 times the derivative of the natural log is 1 over x. So let's set the first derivative equal to 0 to find our critical points. So we would have 1 minus 2 over x equal to 0. So let's see, how are we going to do this? So I think what I'll do is add the 2 over x to the right-hand side. I'd have 1 equals 2 over x. I'll think of 1 as 1 over 1 and use cross multiplication, so x must be equal to 2. So we get x equal to 2 as our critical point, right? So we know that that's a point. In fact, it's the only point on this function where it's defined, and maybe we should think about that a little bit. Because of the natural log, the domain is going to be equal to 0 to infinity. So we couldn't put any negatives in here because the natural log would give us a problem there. And we also can't put 0 in, which is a good thing because the derivative wouldn't allow us to evaluate any slope at 0. So we have a single critical point, and the question is it a relative maximum or minimum? And so we could do this a couple different ways. We could take a look at points before and after 2 and decide whether the thing is coming from below or from above as it approaches 2. Or we could take a look at the second derivative and use the second derivative test. And so I'm going to try the second derivative. So let's try the second derivative test. So I'll give myself some room here and try to find the second derivative. Let's talk about the first derivative, how we could write it a little bit easier for the second derivative. I'm going to write it as 1 minus 2x to the negative 1. And so the second derivative is going to equal 0 plus 2x to the negative 2. So the negative 1 comes out in front, and then we lower the exponent by 1 value. So, so we're at 2 over x squared would be another way of thinking of this. 2 over x squared. And what are we trying to figure out? Well, we're trying to figure out what's going on at 2. Is the concavity up or down? So f of 2, excuse me, f double prime of 2, let's find out what that is. It's 2 over 2 squared. Well, that's 2 over 4. 2 over 4 is, what, 1/2. And the important thing we realize is that that's greater than 0, right? So the second derivative is equal to 1/2, which is greater than 0. And if it's greater than 0, then it must be concave up at this point. So what I assume is that the only critical, extrema that we have it would be a local minimum at 2. And so at x equals 2, we have a local minimum. And my justification is by the second derivative test. I hope that makes sense. If we take a quick look on our graphing calculator at the function, that should confirm. So what do we have? We have x minus 2 times the natural log of x. And I'm going to just do a zoom 6, which is just the standard view. And I can see, I don't know if you can see that very well. Yeah, you can see it all right. I can probably zoom my window in a little bit there, so I'm going to just zoom in by looking. Yeah, let's zoom in on that region of the graph, and it does appear that when x is valued at 2, we do have a local minimum. I could trace it and just type in 2 on the trace, enter, and it seems to have found this small spot on the graph, or I guess the spot on the graph where it's least valued, and that's at, appears to be at 2. So pretty good confirmation using technology of what's going on here. There's some ways also that you can use the calculate function to find a minimum. I'll let you play around with that. Let's go on to our next example, x squared minus 5x. Okay, so intuitive, x to the 5th minus 5x, x to the 5th minus 5x. So let's go ahead and carry this one out. You know, we think first of all it's an odd valued polynomial, so that means it has a positive leading coefficient, right? So I think we think that the thing has, you know, a shape something like this, where, you know, as we go to positive infinity in the x sense, the function should be growing to positive infinity and vice versa for negative. But the question is there any spot in the middle where we actually get some sort of a relative max and min? And this is really, I guess, accentuates this idea of relativity here. You know, that this function is going to grow as big as you want it and as small as you want it if you go far enough in the x direction or negative x direction. But in the middle, it might have some spot where, relative to the points around it, there is a maximum or a minimum. So let's see if we can find those. So I'll go ahead and find oh, and I'm sorry, it's called g, so I'll go ahead and do g. G prime of x is going to be equal to 5x to the 4th minus 5. Let's go ahead and hit the double second derivative. That was going to be 20x to the 3rd. Okay. Well, that's nice because the second derivative is easily evaluated, so it seems like we are going to be quickly able to use the second derivative test. So let's see if we can figure out what's going on here. 5x to the 4th minus 5. Let's set that equal to 0 first. So g prime of x equal to 0. It means that we set 5x to the 4th minus 5 equal to 0 and solve. I'll go ahead and think about this a little bit. Let's take a 5 out of both terms. We get x to the 4th. Minus 1 equals 0. Divide through by 5 and we'd get x to the 4th minus 1 is equal to 0. We could move the 1 across and take the 4th root. That would work just fine. If we do that, we got to be a little bit careful. Another way you could do this is to factor it, but let's go ahead and move the 1 across and take the 4th root. So now think carefully about what this means. If I take the fourth root of x, I get x, and if I take the fourth root of 1, what could, what would that yield? Well, what that yields, and just be aware that either 1 or -1 is a root here. And to convince yourself of that, move back up here and plug a 1 in and make sure that you get 0. Plug a -1 in and make sure that you get 0. And you'll see that that certainly you have to consider both roots in the fourth root here. Okay, so we have two zeros, or I should say critical points. So the critical points of the function are at x equaled 1 and x equal to -1. And we can kind of quickly determine that 1 is a relative max and 1's a relative min. The reason is I can take g double prime of 1, and if I put 1 into the second derivative, I can see that it's definitely greater than 0. And g double prime of -1, if I put -1 into a cubic function, well, that just returns a -1, so you get -20, so it's less than 0. So what can we say based on these results? Well, we can say that g of x has a, let's see, a local, so at x equaled 1, we are greater than 0, let's start from the left, x equal -1, we're less than 0. So if we're less than 0, we're concave down. So it has a local max at x equal -1 and a local min, the opposite, at x equal 1 by the second derivative test, so 2dt. Let's take a look at the graph of the function just to make sure we got it right. I'll clear this out and put in x raised to the 5th minus 5x. So I'll zoom 6 it on my graphing calculator, and sure enough, it does appear that there is a local max and a local min. Let's just zoom in to make sure that we are getting them at the right. We're out of screen. I need a little bit more height and width in my, height in my window. So let's let the y max and min be, what, -5 and 5. There we go. So it does appear at -1 and 1. We have a local maximum and minimum. If I put it in trace mode and just type in -1, enter, you can see my little spider does go to the top of the graph at -1. And if I type in 1, enter, it does appear to go to the minimum spot in the graph. So it does appear that the second derivative test has shown us, without even looking at this function beforehand, where the local maximums and minimums occur. Let's do one more example and end. So what do we have here? We've got a little bit interesting function, 5x e to the -x. So this is h of x. 5x e to the -x. So what's h prime of x? Well, we have a constant multiple, take it out front, and then I have a product. So I'm going to have to use the product rule here. First times the derivative of the second. So let's see here. So it'll be x times e to the -x. So it'll be x times, well, this is a chain rule, so e to the x with the -x put in would be e to the -x times the derivative of -x, -1. So lots of review in this one. We've got a product and a chain going on here. Plus the second times the derivative of the first, that's just going to be e to the -x times the derivative of x, which is just a 1. So cleaning this up a bit, it looks like we have e to the x minus x e to the -x. So 5 e to the -x minus x e to the -x. Okay. Let's go ahead and think about what happens when h prime of x is equal to 0. Well, that's when 5 times e to the -x minus x e to the -x is equal to 0. Okay. And I'll divide through by 5 and just get e to the -x minus x e to the -x equals 0. E to the -x is going to be equal to x e to the -x. If I add the x e to the negative x across. So now I see that I have an e to the negative x both sides. So if I divide through by e to the negative x, I get 1 equals x. So it appears that when x is equal to 1, we have a critical point. So this is our critical point. So it's the only spot in that graph where we'd expect a 0 valued derivative. And now we have a decision, right? We can use the second derivative test or the first derivative test. And in this case, I think it's easier to use the first derivative test. The reason being is that to find the second derivative of this fairly complex first derivative function, it's going to be a little bit more difficult than simply evaluating before and after the critical point, right? So if we know this is the only place where things are valued at 0, then let's take a look at what the values before and after it are. So let's see if I can get this right. Try to make it show up. So what I'd probably do is I'd choose h prime of 0. That's an easy point before x equals 1 to evaluate. If h prime of 0 would be 5 times e to the negative 0 minus 0 times e to the negative 0, right? Well, 0 times anything is just 0, so that goes away. But anything raised to the 0 power is a 1, so we'd have 5 as our value. So what appears is that we're approaching from the left-hand side with positively valued slopes, and I would assume that to the right of 1 we'd have negative valued slope, but let's find out if that indeed is a critical point, or excuse me, a relative maximum is what it looks like at this point. So h prime of 2, let's try that. So it would be 5 times e to the negative 2 minus 2 times e to the negative 2. And if you look here, you have 1 minus 2 e to the negative 2. So 1 minus 2 would be negative 1. So negative 5 e to the negative 2 is what we have. And of course, e to the negative 2 is the same thing as negative 5 all over e squared. That's a positive valued e squared, so you got negative divided by positive, so this is definitely negative or less than 0. So what can we conclude? Well, by the first derivative test, we can say that h has a, let's see, we're approaching to the left, from the left positively, we're leaving on the right negatively, so h must have a relative maximum at x equal 1 by the first derivative test. And let's take a quick look and just see if that's really true. Let's clear this out and put in 5x e, which is above the natural log, e to the negative x. And I'm going to just zoom 6, our standard zoom for right now. And yeah, you can kind of see there's some sort of hump happening in there. Looks like a relative maximum at 1, but let's zoom in on that region. So I'll use my little crosshairs to zoom in on that region. Yeah, it does appear pretty good. Here is 1, and it does appear that, let's go ahead and trace it and just type in 1 in trace mode, and it does appear that the little spider is at the top there at 1. So some good confirmation of what the algebra here has told us. Okay, that's it for this section. I hope that you've gotten some good ideas about how to use the first and second derivative tests. Let me know what questions you have.